In this last lecture, we're going to review topics from the last part of the course, namely sinusoidal steady-state analysis, frequency response, AC power, and RLC circuits. And we'll do this review through a bunch of examples. So basically, this lecture is just a whole bunch of examples. In this first example, we're given an RLC circuit and we're asked to find the Thevenin equivalent. One important thing to note, whenever you have an RLC circuit and you want to find the Thevenin equivalent, it is always frequency dependent. In other words, you need to know the frequency of operation, in this case 10 to the 4th radians per second, in order to do the Thevenin equivalent. It doesn't make any sense to find a Thevenin equivalent if you cannot do it at a particular frequency for AC circuits. So the first step is you want to convert the circuit to its phasor domain equivalent. So the voltage source, which was 10 cosine 10 to the 4th t minus 15 degrees, becomes 10 at an angle of minus 15 degrees volts. The capacitor becomes an impedance of minus j over omega c, so it becomes minus j 10 ohms. The inductor becomes an impedance of j omega l, so it becomes j 10 ohms. The resistor, of course, is unaffected, so it is still 10 ohms. And the open circuit voltage V0 is VOC phasor at this point. Once we set it up as a phasor equivalent, we can now solve it using DC techniques. The only difference, of course, is our numbers are all going to be complex numbers. So the first thing we want to find is VOC phasor. You could use that using whatever approach you want. What we're going to do is we're going to combine these two impedances in parallel, and then we're going to use voltage division. So VOC is J10 in parallel with 10 ohms over J10 in parallel with 10 ohms plus minus J10 ohms. All of that multiplied by 10 at an angle of minus 15 degrees. Combining two impedances in parallel is the product over the sum, so we get J100 over 10 plus J10, all of that over the same thing, J100 over 10 plus J10, minus J10 times 10 at an angle of minus 15 degrees. If we multiply each of these terms, this term, and this term, each by 10 plus J10, we now get, the numerator is just J100, this term is just J100, and this third term is minus J10 times 10 plus J10. Once again, all of that is multiplied by 10 at an angle of minus 15 degrees. You work out this math, it becomes J100 over 100 times 10 at a minus 15 degrees, or 10 at an angle of 75 degrees volts. And we set that aside. We then want to find the Thevenin impedance, Z Thevenin. So that is the Thevenin impedance looking back into these terminals there. With the voltage source shut off, remember a voltage source that equal to 0 is a short circuit. So Z Thevenin now is what? It's going to be minus J10 in parallel with J10 in parallel with 10. When you have multiple things in parallel, it's a reciprocal of the sum of the reciprocals. So it's 1 over minus J10 plus 1 over J10 plus 1 over 10. Turns out these two cancel, and so we end up getting 1 over 110, or just 10 ohms. So the Thevenin equivalent in the phasor domain is nothing more than the open circuit voltage, 10 at an angle of 75 degrees, and an impedance of 10 ohms. If you want to convert this back to the time domain, you can do that. So 10 at an angle of 75 degrees just becomes 10 cosine 10 to the 4th t plus 75 degrees volts. And of course, an impedance of 10 ohms is just a pure resistance, a 10 ohm resistor. So our final answer these two things here. And once again, an important thing to remember, in the AC domain, sinusoidal steady state analysis domain, when you are finding Thevenin equivalence, you have to do it at a particular frequency of interest, in this case 10 to the 4th radians per second. This is the same circuit, and now we're asked two parts. The first part, we're asked to determine the type of filter without actually computing its transfer function. In other words, just from inspection, we want to look at this circuit and figure out, is it going to pass the low frequencies, the high frequencies, or frequencies in the middle, and from that we can figure out what type of filter it is. And then, for given values of resistor, inductor, and capacitor, same values as on the previous page, we then are asked to find an actual expression for the transfer function. So to do it without actually computing anything, what you need to do is think about the two extremes, at low frequencies and at high frequencies. At low frequencies, what do we know? As you get close to zero, capacitors start looking like open circuits, and inductors start looking like short circuits. So at low frequencies, basically, we get that open there. That is shorted out. You have a resistor there. And this becomes what the circuit looks like. And it's pretty obvious to see that because of this shorted out inductor, that V out is equal to 0, regardless of anything else. At high frequencies, capacitors now become short circuits. Inductors now become open circuits. So revisiting this, the capacitor becomes a short circuit. The inductor becomes an open circuit. Resistor is unaffected. Now what we see is that you just have wires connecting the input directly to the output. So we see that V out is going to equal V in. So from this we see at low frequencies the output is 0. At high frequencies the output is just going to match the input. So we can see from inspection that this is a high pass filter. In the second part of this problem, we're now actually going to calculate the filter's transfer function. So we see that the output phasor over the input phasor, which by definition is the transfer function, is what? Well, we could use voltage division like we did on the previous page. These two are in parallel. So we end up getting H omega is going to be the resistance in parallel with the inductor's impedance. The inductor's impedance is J omega L, so J omega over 1,000 over the same thing plus the capacitor's impedance. The capacitor's impedance is minus J over omega C. So it's minus J 10 to the 5th over omega. You work out the math. Remember, things in parallel, it's a product over the sum. So 10 in parallel with J omega over 1,000 is a product, which is J omega over 100 over the sum, 10 plus J omega over 1,000, all over the same thing, minus J 10 to the 5th over omega. From here, what we're going to do is multiply each of these three terms, that one, and that one, by 10 plus J omega over 1,000. So it's going to cancel in that term, it's going to cancel in that term, and then in this term we're going to have to actually multiply that out. So we now get this equaling J omega over 100 over j omega over 100 minus j 10 to the 5th over omega times 10 plus j omega over 1,000. Now we're going to multiply all three of these terms, this one, and this one, by 100 to get j omega over j omega minus j 10 to the 8th over omega plus 10 to the 4th. Finally, let's multiply the numerator and the denominator each by omega to get our final answer of h of omega is j omega squared over j omega squared minus j 10 to the 8th plus 10 to the 4th omega, which we can now rewrite in our final form, j omega squared over the real part of the denominator is 10 to the 4th omega, and then combine the j terms plus j times omega squared minus 10 to the 8th. So in this problem, we first guessed what the frequency response was going to be just by looking at it at the low end and the high end, and we saw it should be a high pass filter. And then in the second part, we actually calculated the transfer function. Now that we have the transfer function, we can now calculate the output for a specific input. So from before, from the previous page, we know that the frequency response h of omega was what? J omega squared over 10 to the 4th times omega plus j omega squared minus 10 to the 8th. This is from the previous page. Now we're asked to find the output for a particular input. The particular input was 8 cosine 10 to the 3t minus 50 degrees. So the frequency of operation is 1,000 radians per second. So what we need to do is evaluate h of omega at 1,000. We end up getting j times 10 to the 6th over 10 to the 7th minus j 10 to the 8th minus 10 to the 6th. You work that out, it's j over 10 minus j99, which in polar form is 0.01005 at an angle of 174.23 degrees. So what we see is that this will get multiplied by the input magnitude to get the output magnitude, and this angle will get added to the input angle to give us the output angle. So V out of t is going to be 8 times 0.01005 times the cosine of 10 to the 3t minus 50 degrees plus 174.23 degrees, or 0.0804 cosine 10 to the 3t plus 124.23 degrees volts. So once again, once we had the transfer function, we can now evaluate this circuit for any input at all just by using the transfer function. We don't need to go back to the circuit itself because we basically did that already with this general transfer function. If we now take this frequency response and create its Bode plot, that's going to show up on the next page. So the Bode plot of this circuit is as follows. And once again, we see that it is a high-pass filter. For high frequencies, it passes. For low frequencies, it attenuates with this break point at 10 to the 4th radians per second. But now we're asked to use the Bode plot to determine the output voltage when the input is as follows. And notice we have inputs at 1,000 radians per second, 3,000 radians per second, and 4 times 10 to the 6 radians per second. So what you want to do is find all of these frequencies on the Bode plot. 10 to the 3 is this point. So this is right there, which is approximately minus 40 dB, which of course minus 40 dB is a gain of 0.01. And its angle is there. And boy, it's pretty close to 180 degrees. We'll say it's approximately 175. We're just eyeballing it. 3,000 radians per second. So this is 1,000, 2,000, 3,000. That is this point here. So that is approximately minus 20 dB, which is a magnitude gain of 0.1. Its angle, once again, it's a ballpark figure. It's maybe approximately 160 degrees. 4 times 10 to the 6, here's 10 to the 6, 2 times 10 to the 6, 3 times 10 to the 6, 4 times 10 to the 6. It's approximately 0 dB, which is a gain of 1. And the phase, approximately 0 degrees. So these are all estimates here. It needs to be pointed out that these are just estimates. For example, we saw at 1,000 radians per second that the gain is approximately 0.01. We saw that the magnitude of H evaluated at 1,000 from the previous page was actually 0.01005. So it's close, but not exact. Furthermore, if we were to do this at 3,000, H of omega evaluated at omega equal 3,000, the gain is actually 0.094. Once again, close to 0.1, but not exact. So the bottom line is the Bode plot gives us approximations, which are going to be close to the actual value, but not right on it. Anyway, continuing with this problem now. So V out of t is approximately equal to, and once again, it's only an approximation because we're using the Bode estimates now. So approximately equal to, the 1,000 radian per second term is going to be multiplied by 0.01, so we're going to get 0.08 cosine 10 to the 3t. Minus 50 degrees plus 175 degrees is going to be plus 125 degrees. The second term, the magnitude of the input was 2 at 3,000 radians per second. That gets multiplied by 0.1, so we get 0.2 cosine 3 times 10 to the 3t plus 20 degrees plus 160 degrees, so plus 180 degrees. And of course, 180 degrees, we could code that with a minus sign here instead of the plus and get rid of the 180 degrees. We don't need to do that, however. Third term, at 4 times 10 to the 6 radians per second, and we're missing a t here. There should be a t in there. That gets multiplied by 1, so we get plus 4 cosine 4 times 10 to the 6 t minus 30 degrees plus 0 degrees. So no change in the angle. So here's our approximation. And once again, what we see is that at high frequencies, there's no attenuation. At middle frequencies, there's some attenuation. And at low frequencies, there's lots of attenuation. Once again, this is a high pass filter. It's passing the high frequencies and sort of blocking the lower frequencies. In this problem, we're asked to actually use nodal analysis to determine the node voltage V1 phasor. Notice this is already in the phasor domain, so we don't need to convert anything. It's already in the phasor domain for us. And basically, we set it up just like we would if this was a regular resistive circuit, except now all of our calculations are going to be in complex numbers. So using nodal analysis, basically you're doing KCL at the different nodes. So we basically have that node is ground. So basically we're summing up this current plus that current plus that current is equal to 0. The current to the left is what? It's V1 phasor minus the voltage at this point, which we're given because it's a voltage source. So 4 plus J3 all over that impedance, which is 10 ohms. That current is V1 tilde over its impedance, which is minus J5. Plus that current. Because we have this current source here, we know the current in that branch already. It's going to be negative 0.2 minus J.1. So minus 0.2 minus J.1. Some of those currents all equal 0. Let's group all of the terms that have the V1 in them. So V1, we get 1/10 minus 1 over J5. And move everything else to the other side. We get 0.2 minus J.1 plus 0.4 plus J.3. 1/10 minus 1 over J5, you work out that's 0.1 plus J.2. So V1 phasor is going to be, let's see, 0.2 plus 0.4 is 0.6, minus J.1 plus J.3 is plus J.2, all over 0.1 plus J.2. You work out this math, you get 2 minus J2, which in polar form is 2.83 at an angle of minus 45 degrees volts. So in the second part of this problem, we're asked to sketch all the node voltages on the phasor diagram. And there are 3 node voltages. There's this one, which is given, 4 plus J3. There's this one, which we just solved for. And there's this third one. We'll call this voltage VC phasor. Okay, so the first one, 4 plus J3, and we're told that each of these blocks is 1 volt, so 1, 2, 3, 4, plus 1, 1, 1. So this is VA, we'll call it. V1, we just solved for 2 minus J2, 1, 2, minus J2. So V1 phasor is that. Finally, what about VC? Well, we see that there's going to be a voltage drop across this J40 ohm impedance, and that voltage drop is what? It's going to be J40 times 0.2 minus J.1, which equals J8 plus 4. So we can see that VC phasor is going to be V1 phasor plus J8 plus 4. V1 phasor was 2 minus J2 plus 4 plus J8. We get 6 plus J6, or 8.49, at an angle of 45 degrees. 6 plus J6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We get our third phasor VC that looks like that. So the phasor diagram has our 3 voltages, VC, which is that one there, VA, which is that one there, and V1, which is that one there. In the final part of this problem, we were asked to find the power delivered by the current source. So now we're looking at an AC power problem. So if you remember when we talked about AC power, if you have any component and you know the voltage across it and the current through it, you can find its power using the power equation. The voltage across the current source is VC phasor, which we calculated above to be 8.49 at an angle of 45 degrees volts. The current through the current source, it's 0.2 minus J.1 going up, so the current going down is the opposite of that, so it's minus 0.2 plus J.1 amps, which in polar form is 0.224 at an angle of 153.4 degrees amps. So the absorbed power, the average absorbed power, is what? We need the 1/2 term because we're not looking at RMS voltages here. So 1/2 times the voltage magnitude, 8.49, times the current magnitude, 0.224, times the cosine of the difference between the angles. 45 degrees minus 153.4 degrees is minus 108.4 degrees. You work out all this math, you get minus 0.3 watts. That means that it is supplying power, so the final answer is 0.3 watts supplied. So in this problem, we're asked to use mesh analysis to determine the current through the voltage source. And just like the nodal analysis problem, our circuit is already given in phasor form, so we don't need to convert anything to phasor form. It's already given that way. So we can just follow the DC algorithm for mesh analysis, except we're going to be using complex variables and complex numbers. So there are two meshes. This left mesh, we do not know the current, so we're going to give it a variable, I1. The right mesh, we actually know the current because there is a perimeter current source. It's actually counterclockwise with a value of 0.2 and an angle of 0 amps. So now let's do KVL along this left mesh. We're going to sum the voltage drops. So we get what? We get minus 5 at an angle of 36.9 degrees, plus the voltage drop across the 10 ohm resistor, so it's 10 times its current, which is this unknown variable I1, minus J5 times the current through this, and basically we have a current of I1 and then a current of 2 at an angle of 0. So it's I1 plus 2 at an angle of 0. The sum of all those voltages is equal to 0. So we get I1 times 10 minus J5 is equal to, bringing to the other side, we get 5 at an angle of 36.9 degrees plus J1. So I1 becomes 4 plus J4 over 10 minus J5, which is equal to 0.16 plus J0.48, or in polar form, 0.506 at an angle of 71.6 degrees amps. So in the second part, we're told what the value of Vx is. Vx is the voltage across this unknown impedance. We're told the voltage from the phasor diagram, and we're asked to find the voltage across the current source. So we're asked to find this voltage here. Let's call this Vs phasor. So we're given Vx. Notice the scale here is each of these blocks is 0.1 volts, so it's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. It's 0.6 plus J.4 volts is Vx. Now, if we do KVL along this outer loop, voltage drop plus voltage drop plus voltage drop plus voltage drop is equal to 0, we get what? We get minus 5 at an angle of 36.9 degrees. The voltage drop across the 10 ohm resistor is 10 times its current, I1, but we know what I1 is. It is 0.16 plus J.48. We solved that in the previous part of this problem. Minus Vx. Vx we're given there. It's 0.6 plus J.4. Plus what we're solving for, Vs is equal to 0. The only unknown is Vs. We could solve for Vs. We get Vs is equal to 5 at an angle of 36.9 degrees minus 1.6 minus J4.8 plus 0.6 plus J.4. You work out the math. You get 3 minus J1.4 volts. In the final part of this problem, we are asked to compute the average power absorbed by Zx. Zx is this unknown impedance right here. We don't know the impedance, but we know the voltage across it from the phasor diagram, and we know the current through it because Zx is in series with the current source, so we can find the impedance as voltage divided by resistance. So in other words, if you know the voltage across the element, in this case it's 0.6 plus J.4 volts, and we know the current through it, 0.2 at an angle of 0 amps, we know that Zx has to be what? The voltage divided by the current, you get 3 plus J2. So in other words, this unknown impedance is going to be a resistor and an inductor. The resistance is going to be 3 ohms. We know that all the power absorbed is absorbed by the resistor. And so the absorbed power is what? It's 1/2. Why 1/2? Because we're not working with RMS values here. 1/2 times the current magnitude. We already determined that the current magnitude was what? 0.2. 1/2 times the current magnitude squared times the real part of the impedance, or 3, and we get 0.06 watts. We could have also have found the power from using the power equation and this voltage and this current. This page has a couple AC power problems, so we're basically given the Thevenin equivalent of a circuit here on the left, and it's driving a load ZL. So in the first part of the question, we're asked to determine the power absorbed by the load if the load is 3 plus J4 ohms. Then we're asked to determine what the load impedance would have to be to get maximum power transfer, and then calculate that power as well. So in the first case, we have the following. We have a voltage, 10 at an angle of 30 degrees. We have an impedance, 2 minus J2, and we have an impedance, 3 plus J4. So the current through the load, call it IL, from Ohm's law, is 10 at an angle of 30 degrees, divided by the total impedance. 2 minus J2 plus 3 plus J4 is 5 plus J2. So the total current is 1.857 at an angle of 8.2 degrees amps. So to find the power absorbed by the load, there are a couple ways you can do it. One, you could find the voltage across the load and then use the power equation. But we actually don't need to do that, because if you know the current through the load and you know the real part of the load, you can use the simplified equation. So the power absorbed by the load is what? It's 1/2. Once again, we need the 1/2 because we're not talking about RMS voltages here. So 1/2 times the magnitude of the current squared, 1.857 squared, times the real part of the impedance, which is 3, or 5.173 watts. In the second part of the problem, we're asked to determine the load impedance that would give us maximum power transfer and then calculate the power in that case. So to get maximum power transfer, you said ZL equal to the conjugate of the Thevenin impedance. So you set it equal to 2 plus J2 ohms. So now we're left with this situation here. 10 at an angle of 30 degrees, 2 minus J2, 2 plus J2, and we have that. Well, we could calculate the load power multiple ways here. The easiest way is know that when you have maximum power transfer, the power absorbed by the load is what? It's the magnitude of the open circuit voltage squared over 8 times the real part of the Thevenin impedance. Once again, this equation here can only be used in maximum power transfer. So we could not have used this equation in the part above, but we can use it now. It equals what? VOC, 10 volts, so you get 100 over 8 times 2, or 6.25 watts. We can check that answer by calculating the current going through the load and then using a different equation. So the current through the load, I, is what? 10 at an angle of 30 degrees divided by 2 plus J2 plus 2 minus J2, or 4. So it's 2.5 at an angle of 30 degrees. One thing to note here, whenever you have maximum power transfer, the current is in phase with the Thevenin voltage. That's one of the features of maximum power transfer. Because the imaginary part of the impedance of the load cancels with the Thevenin impedance, you're always going to get the current in phase with the voltage. So the power absorbed by the load is what? It's 1/2 times the current magnitude squared, 2.5 squared, times 2, or 6.25 watts. So once again, the power using the simple equation is 6.25 watts. Using this equation, it's also 6.25 watts. A third way we could have done it, we could have calculated the voltage across the load and then used 1/2 times the magnitude of the voltage times the magnitude of the current times the cosine of the difference between the angles. But we don't need to use that here because we have this really simple equation and this somewhat simple equation. This last problem is an RLC transient response problem, and it is one of those more difficult ones because the variable we are ultimately looking for is not VC or IL, but a different variable. So this represents one of those most time-consuming, difficult, step-intensive problems that we have in EE 210. So it's a good example to finish the semester with. Before we tackle this problem, the first thing we want to do is look at the circuit diagram and recognize that neither VC nor IL is predefined. If they're not predefined, we have the freedom to give whatever orientation we want, but we want to be consistent then throughout the problem. So for VC, I will put the plus on the left and the minus on the right. No magical reason to do that, but that's what I decided to do. For IL, because VL is already defined, it makes more sense to define IL as going down. This satisfies the passive sign convention. Remember, the voltage across the inductor is equal to L times the derivative of the current through the inductor. This is only true if the current is going from the plus to the minus terminal. So by choosing IL going from top to bottom, we preserve this relationship here. Okay, first thing we want to do in this problem, now that we have that out of the way, is to solve the DC steady state problem before the change in the circuit. The change in the circuit happens at time 0, the current source turns on, and the voltage source turns off. So 0 is where we have the change in the circuit. So at t equals 0 minus, we have a DC steady state problem. The voltage source on the left is on, 10 volts. The capacitor in DC steady state is an open circuit. The inductor in DC steady state is a short circuit. Then we have this resistor, and this current source on the right is currently off. And of course, we defined our variables. VC we defined that way, IL we defined that way, and VL, which was given to us at the start of the problem, is that. We need to find all three of these values at 0 minus. So VC of 0 minus, well, the voltage at this terminal is going to be 10 volts higher than the voltage at that terminal, because basically you have the negative terminal of the 10 volt source is tied in directly to that, and the positive terminal of the 10 volt source is tied to that terminal. So VC of 0 minus is 10 volts. IL of 0 minus is going to be 0 amps. Because of the open circuit, no current can flow. Likewise, VL of 0 minus, because the inductor is short-circuited, VL of 0 minus is going to be 0 volts. Now we know that the voltage across the capacitor cannot change instantaneously, so VC of 0 plus is also equal to 10 volts. Likewise, IL of 0 plus is also equal to 0 amps, but VL of 0 plus does not equal 0 volts, at least not necessarily. We may find that it could possibly equal that, but there's nothing that says that it has to equal 0 volts. Once we have the initial conditions, we now want to redraw the circuit for t greater than or equal to 0, and then see what it looks like at time infinity and come up with our final conditions. So for t greater than or equal to 0, what do we have? So now the voltage source is off. We have our capacitor, we have our inductor, we have our resistor, and now the current source is present, and it is a 1 amp source for t greater than and equal to 0. And of course, what we're ultimately looking for is VL, and we have our other variables, IL and VC. We have a 10 ohm resistor, a 1 Henry inductor, and a 10 millifarad capacitor. So as t goes to infinity, once again we have another DC steady state problem, but now the circuit looks like this. The capacitor once again is open circuited, the inductor once again is short circuited, we have our resistor, and we have our 1 amp current source. So we have VC at infinity, IL of infinity, and also VL of infinity. VC of infinity, once again because the inductor is short-circuited, we see that VC of infinity is going to be 0 volts. IL of infinity, what happens? The current coming out of this current source is all going to want to go through the inductor, so IL of infinity is 1 amp, and VL of infinity, once again because the inductor is short-circuited in DC steady state, VL of infinity is going to be 0 volts. The next decision we have to make is whether we want to solve for VC or IL. Remember, ultimately we want to solve for VL, but in the meantime, we solve for either VC or IL, and then in the last step, convert VC to VL or IL to VL. So we have a choice here, and it doesn't matter which one you choose. I'm going to solve for VC. So I'm going to solve for VC. And then in the last step, I'm going to convert that to VL. Alternately, I could have solved for IL of t and in the last step converted IL of t to VL of t. It really doesn't matter, but in this case I'm going to solve for VC first. So the next step is we want to come up with the characteristic equation. Once we have the characteristic equation, we can determine the roots and determine the form of the solution. So if you look at the characteristic equation, we have what amounts to a parallel RLC circuit. So the capacitor, the inductor, and the resistor are all in parallel. And remember, we look at the source-free equivalent to determine that. So you turn off this source, this 1 amp source, and you see that the capacitor, inductor, and resistor are all in parallel. In the parallel case, the characteristic equation is S squared plus 1 over RC times S plus 1 over LC is equal to 0. Plugging values in for R, L, and C, we get S squared plus 10S plus 100 is equal to 0. Using the characteristic equation, the roots are negative 10 plus or minus the square root of 10 squared, 100, minus 4 times 100, all over 2. We see that there are complex conjugate roots. We get minus 10 plus or minus the square root of 300 over 2, which is equal to minus 5 plus or minus j 5 root 3. What that means is that the voltage across the capacitor is going to be Vc of infinity plus e to the minus 5t times d1 cosine 5 root 3 of t plus d2 sine 5 root 3 of t. We saw from before that Vc of infinity is 0. If Vc of infinity was something other than 0, we'd have to plug that in here before we solved for the d1 and d2 coefficients. To find d1 and d2, we need two initial conditions. We need Vc of 0 plus and Vc prime of 0 plus. Vc of 0 plus we have already. It's 10 volts from the previous page. Vc prime of 0 plus we now need to solve for. So how do we solve for that? Well, if you look at the circuit, for t greater than 0, it looks like that. Vc was defined as that. IL was defined as that. IR is the current through the resistor, that's that. And we have the 1 amp source. Vc prime of t is what? It's 1 over C times the current through the capacitor. Current through the capacitor is defined as that direction there. Once again, once we define Vc, the direction of IC is defined for us. But what's IC? This current equals the sum of that current plus that current plus that current. So IC is equal to IL of t plus IR of t minus 1 amp. So what we want to do now is express everything on the right in terms of either IL or Vc. IL is already in terms of itself. How about IR? IR is what? The current through the resistor is its voltage, VR of t, divided by its resistance, where VR is defined as that voltage there. But VR, in turn, is minus VC of t. Once again, if you look at how we defined VC with the plus on the left and the minus on the right, it's the opposite of how we define VR. So VR is just minus VC. So that means that VC prime of t is 1 over C times IL of t minus VC of t over R, which is 10 ohms, minus 1. So VC prime of 0 plus is 1 over C. So the capacitance was 10 millifarads, so it's 100, times IL of t at 0 plus, which is 0, minus VC of 0 plus is 10 volts, so 0 minus 10 over 10, minus 1. So you do all that work, you get minus 200. We now have our second initial condition. We can now solve for D1 and D2. To solve for V1, we see that VC of 0 plus, which we know is 10 volts, it equals what? Plugging into this equation here, it's e to the 0 times D1 cosine of 0 plus D2 sine of 0. Sine of 0 is 0, cosine of 0 is 1, e to the 0 is 1. We end up getting that D1 is equal to 10. To find D2 then, we know that VC prime of 0 plus, which was minus 200, was equal to the derivative of this expression here at time 0. So remember, the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. So the first, e to the 0 times the derivative of the second. The derivative of cosine is minus sine, so minus 5/3 times d1 times sine of 0, plus the derivative of sine is cosine, so the 5√3 comes out of that, times d2 cosine of 0, plus the second times the derivative of the first. The derivative of the first, the derivative of e to the minus 5t is minus 5, e to the minus 5t evaluated at time 0, times d1 cosine of 0 plus d2 sine of 0. Once again, a lot of things evaluate to either 0 or 1. E to the 0 is 1, sine of 0 is 0, cosine of 0 is 1, cosine of 0 is 1, sine of 0 is 0, and e to the 0 is 1. So now solving for d2, we get minus 200 is equal to what? 5 times the square root of 3 times d2 minus 5 times d1. But what is d1? d1 is 10, so we end up getting that minus 150 is equal to 5 square root of 3 times d2, or d2 is equal to minus 150 over 5 times the square root of 3, which is equal to minus 30 over the square root of 3, which is equal to 10 square roots of 3. So from this we have that VC of t is e to the minus 5t times 10 cosine of 5√3 times t plus 10 times the square root of 3 times the sine of 5 square root of 3 times t volts. But we are not done yet, because remember, we were not asked to find VC, we were not asked to find IL, we were asked to find VL. So the very last step is we want to find the relationship between VL and VC for t greater than or equal to 0. Fortunately, this is very simple. If you look at this equation here, VC is this voltage here, VL is this voltage here. The capacitor and the inductor are in parallel. The only thing is that VL has an opposite polarity of VC. So we see that VL just equals minus VC. So this last step is very simple. Our final expression then is VL of t. For t less than 0, it's 0 volts. We solve that way back there. For t greater than 0, it's the opposite of VC of t. So it's going to be e to the minus 5t times minus 10 cosine of 5 square root of 3t minus 10 square root of 3 sine 5 square root of 3t. And that's valid for t greater than or equal to 0 seconds. One thing you might want to do to check to make sure your answer is correct is look at VL of 0 plus and look at VL of infinity to see if they agree with what we saw earlier. VL of 0 plus, at 0 plus, this term is 0, this term is 1, so we just get minus 10. Notice that that does not equal VL of 0 minus. Remember, we said way back here that they didn't have to be equal, and sure enough, they are not equal. VL of infinity, if you plug infinity into this expression here, what happens is the e to the minus 5t goes to 0, so VL of infinity is 0 volts, which does indeed agree with what we expect to have here. So that check doesn't prove that our answer is correct, but at least it sort of gives us some validation that it probably is correct. So our final expression for VL of t is given by this expression here. So as I warned you at the beginning of this problem, these RLC circuits are very time-consuming problems. There are many, many steps. And this one is particularly tough because what we're ultimately looking for is not VC or IL, but in this case, VL. Nevertheless, if you break it down into the individual parts, finding initial conditions, finding final conditions, finding the form of the characteristic equation, finding the roots of the characteristic equation, using that to find the form of the solution, finding our two initial conditions we want to use, in this case VC and VC prime is 0 plus, and then plugging those in to this equation here to solve for D1 and D2, and finally finding the general relationship between VL and VC, we come up with our final equation right here.